Hello again. Let's go ahead and continue on with some more derivative applications. And here we're going to be talking about optimization. Before we actually get into the idea of what optimization actually is, we're going to do a little recap of extrema. And so really when I say extrema, I just mean a fancy word for maximums and minimums. So let's go ahead and first recall the first derivative test. So remember that this first derivative test tells us if our critical numbers are maximums or minimums. And so what we were doing in here is, we were making a number line, and once we had this number line, for f prime, obviously, we would go ahead and we would plot a critical point. I'll label it x sub c, and then we do some test points here. We would come up with some test points, and when we actually plug those into the derivative, we got something maybe like a plus and a minus, something positive and something negative. And so that would tell us, that would indicate at least that our function increases and then it starts to decrease, which means that I'm definitely going to have a max right up there. And then if it was minus and plus instead of plus and minus, that would indicate a minimum. But this was the first derivative test. This tells us whether our critical numbers indicate a maximum or a minimum. What we're going to take a quick look at in a second is what happens actually if our number line indicated something like, what if we had a plus and a plus instead? So we could have a critical point, but it doesn't have to change sign here. We'll see some different examples of these critical points and different things that sort of can happen. So what I emphasize down here in the second bullet point is that when we find these critical numbers, we might find maxes and mins. They don't have to be maximums and minimums. So I say that word might. We'll sort of look at examples here. So first thing that I want to recall here is actually what the conditions of a critical number are. So critical numbers, I'll go ahead and write that here. Critical numbers, we need f prime of that critical number to be equal to 0 or f prime of that critical number to be undefined. And if that's the case, then that point is actually a critical number. It is a critical point. And so what we'll see here is basically, we'll see, okay, there's two different ways that we can have critical numbers. And then when we're talking about relative extrema, there's sort of a handful of options for different types of extrema that we could have. So we could have a maximum. We could have a minimum. And in fact, also we could have no extrema. Obviously, no extrema is not a type of extrema, but I'm just emphasizing the fact that we don't necessarily have to have an extrema here. And so really what we're going to look at is we're just going to look at these sort of scenarios all mixed together, if you will. And let's go ahead and take a look at these. So first scenario of I believe we're going to have 5 scenarios here. Yeah, we'll have 5 scenarios. So the first scenario that we'll talk about here is if you have your derivative equal to 0 and if you have a maximum for your critical point. That's going to look like this. That's going to look like this. I don't want to use the word parabola, but it's going to look like this curve. I don't say parabola because it could really be any function, but it looks like this sort of concave down curve. It looks like it's frowning, right? We've got that frown going on right there. And so this is a case where our derivative is equal to 0 right at that point. So you can see we have a tangent line right there that has a slope of 0. I'll indicate m equal to 0. And in this case, we have a maximum. And we could compare this to our second case here, where it's basically the same thing, but instead we just have a minimum. And so if we just label that there, now again, we've got our concave up right here. It is smiling. And actually, while as I said concave up, I realized I think back here I verbally said concave up, but this would be concave down. We'll hopefully remember that. This would indicate a negative second derivative if it's frowning. So negative second derivative on that maximum case, positive second derivative on this minimum case. And so really with these two examples, I'm just showing you, hey, these are things that can happen when you have a critical point. So if I have a critical point, and in this case where the derivative is equal to 0, then that's going to sort of lead me to two other options where I could have a maximum or I could have a minimum. And so there we go. That's our first two examples right there. The third case I want to actually talk about is still going to deal with when f prime of x is equal to 0, but that's going to be when I actually don't have an extrema. So what I'm showing here is the possibility of having a derivative equal to 0 here, right at that point. Let me draw this carefully. So we'll have a tangent line with a slope of 0. But as you can very clearly see on this graph, there is no maximum or minimum at that point. And this is a perfect example of where my function is always increasing. And so if I were to draw a number line, it might look something like what we saw earlier. Let's go ahead and just squeeze this in right here. I might have a number line where at that critical point it's positive and positive on both sides, and that could look something like this graph right here. So what I'm showing here is this graph is a perfect example of when you can have a critical point, but you don't have to have an extrema. Let's move on to the case where we could have a critical point where our derivative does not exist. And so what we would see here is at this point right there, we have a vertical tangent line. And so m is going to be equal to infinity there. Let's go ahead and mark that. So m is equal to infinity there. You could also say just the slope does not exist. And again, we see here, this is a case where we don't have a maximum or a minimum. This point right here is not a max or a min. And again, our number line, if we were to draw it for this, it would look somewhat like this. Obviously, just sketching this out. We would have that same plus on both sides of that critical point. So yet another set of scenarios where I could have a critical point, but not have an extrema. And so we're seeing here, this would be a scenario where I do in fact have a critical point right there, but there's no max or min. And then same here, I have a critical point, obviously in a slightly weirder case with this does not exist rather than 0, but I also don't have an extrema. So this is going to bring me to our fifth and final example. And before I move on there, I just want to recap these first four. So in these first two, what we looked at was we said, all right, I have a critical point, number 1, and I have an extrema, number 2. So in here, I have a critical point and I have an extrema. Also here, I have a critical point and I have an extrema. In the cases 3 and 4, I have a critical point, but in fact, I don't have an extrema, right? So really what we're seeing is, so far, extrema aren't really necessitated by having a critical point. You could have a critical point or not, or excuse me, you could have a critical point and then you could have extrema or not have extrema. What I want to now mention here is how you can have extrema if you don't even have a critical point. So these first 4 are saying, hey, we're assuming that we have a critical point, and now we're looking at all the possible cases of what our extrema could or could not look like. Now let's look at what happens when we do not have a critical point, but we still have an extrema. And this is a weird case. This is a little fishy, might be the word. A lot of mathematicians debate and fight over this, but in this case, what we'll see here is because of these endpoints, we're going to say that this function has a maximum on this right side. So I'll label that. I would call this a relative max. And then here, I would call that a relative min. And so in this case, we have a max or a min, and we don't have a critical point, right? The derivative of this function is never equal to 0, yet we still have maxes and mins. And so that's a perfect example of a case where you can have extrema without having a critical point. So let's sort of recapping all of this and relating it kind of to the first derivative test. We have these 2 points. Extrema, so a max. When I say extrema, I just mean max or min. So max, min. So just maxes and mins can only occur when f prime of x is equal to 0. That's one scenario, and we saw that back here on these first and second cases. So when f prime is 0 and we have a minimum, I'll note coming back here, sorry, I'm flipping around a lot. So extrema can occur when f prime is 0. Notice that I don't say when f prime does not exist. Remember, we looked at this case. When f prime does not exist, you have a vertical tangent line. And what that will mean is that you can't have a maximum or a minimum there. It's just not possible. So I leave that out here. I do not include and f prime equals dne. I don't want to put that in there because when f prime does not exist, that does not yield an extrema. So extrema occur when f prime is 0 or at these endpoints, which we saw in this scenario where I don't have a slope of 0 anywhere in here. But because of my endpoints, I do have relative maxes and relative mins. The second point that we'd say is that if I set f prime equal to 0, that does not necessarily give me a minimum or a maximum, and that is perfectly described by this scenario here, this function. I have a derivative equal to 0 at that purple dot, but I do not have a maximum or a minimum. What I really want to emphasize is this idea of extrema occurring at f prime or at endpoints. This right here is really the sort of the big ticket item for so far what we've seen. And so I'll give an example. So I'm a runner. I run a lot of races. And if someone might ask me, they say, hey, you ran that whole race and you had a certain speed during the whole time of the race, and in the middle of the race, your speed increased, maybe it decreased, maybe I went down a hill, so I ran faster, and maybe I went up a hill, so I ran slower. But what if someone asked me, all right, at what point in the race did you run the slowest? Well, if you tried to find a scenario where my speed was decreasing and then my speed was increasing, that would be great, because then you could find that point right there and you could say, well, hey, you went from decreasing, right, from going really slow to increasing your speed. So this down here at the bottom had to have been your slowest speed, right? And that would be fine, except for the fact that what I want to recognize is that the slowest point, my slowest speed in the race, was actually the moment that the race started. I wasn't running at all right when that race started. And that's a perfect example of this end point right here. So what I would say if someone asked me, hey, at what point in the race did you run at your slowest speed? I don't want to tell them, oh, well, I ended up running 5 miles an hour at 10 minutes into the race. And yeah, sure, maybe for the rest of the race I was faster than 5 miles an hour, but I don't want to say that because I actually ran 0 miles per hour in the beginning. And what that all looks like graphically is sort of there's these sort of two scenarios here that I'll graph. So the first scenario being just something kind of normal. I have a function, and let's just look on this interval a to b. So I have a function and it goes like this. Yay, that's what it looks like. And so it's very clear and very easy to recognize here that, hey, that's my max, that's my min. But if I give you a function where, again, let's just look at this interval a to b here. If I give you a function that looks like this, and you ask, hey, where's the max, where's the min? You do not want to say that this is the max because it clearly is not the max, right? The max is clearly right there. And again, you don't even want to point to right there because obviously, you could keep pointing higher and higher and higher right up until you got to that point right there. And so that maximum is going to be right there at that top, and the min is going to be right there at the bottom. So we do want to be careful about endpoints here. So keep that in the back of your mind, that extrema occur at f prime equals 0 or at endpoints. What you hear a lot of mathematicians say is extrema occur at critical points and endpoints. They can occur at either of those. So there we go. We've got that. Now let's go ahead and look at an actual optimization example here. So this is going to be actually getting into these problems and talking about what's going on here. So we're going to first look, like we did with related rates, we're going to first look at an example that does not involve an application. Similar to related rates, we won't see very many of these, but I like starting off with this example because it's sort of just equations and math. We don't have to worry about a word problem or anything like that. And so what we're going to see here is I'm going to give us, let's say we have two numbers that are labeled by X and Y. They're represented by X and Y, and they satisfy this equation, which I'm going to call a constraint equation. So right here, this right here will be called a constraint equation. And the reason we call it that is because there's sort of restrictions. There's a constraint on how X and Y are related based upon this that I've boxed in the red. And so if I chose X to be something, this equation right here, it constrains Y, it restricts Y to being a specific value. And that's why we call it a constraint equation. The next thing that I want to mention is that we're going to maximize the quantity f. So f is a function, and it is a function of X and Y. I could write this as f of xy equals xy squared. That would be perfectly viable. It would be a function of two variables. We're used to seeing functions of one variable. But in this case, really just what I'm saying is, hey, I've got this quantity that is just whatever X is multiplied by whatever Y squared is. And I want to make that as large as I possibly can. And this right here, this quantity, well, actually, let's label this as an equation. We're going to call this our optimization. Let's do that in a different color. Our optimization equation. And so there we go right there. I'll make sure these colors match. So optimization equation right there, and those are our constraint equation. We want to know what X and Y are. So let's go ahead and work through this slowly. The first thing that we want to recognize is that we're trying to maximize this quantity xy squared. And so what our mind should be thinking about is when we see that word maximize, we should be thinking, all right, there's two scenarios that I can have a maximum for a function. I can have a maximum when I have a f prime of x equals 0, or when I am at an endpoint, right? And so for the first one, f prime of x equals 0, that indicates some sense of a derivative here. And so maybe we get to this idea that actually, well, let's leave that there. So maybe we get this idea in our heads that, all right, I've got f equals xy squared. Let's take a derivative of it. But here's the problem. As I mentioned before, this is currently a function of two variables. There's two variables here, and I don't like that for taking a derivative. We don't know how to take derivatives of functions when there's two variables in there. We've done implicit differentiation. That's a little bit different because that's in that scenario, y is a function of x. In this scenario, I'm actually saying, hey, my two variables are just, they're different. X and Y are just two completely different numbers. They're not dependent on each other at all. And so this is tough. We don't know how to take a derivative of two variables. So what we would want to do before we have this notion of taking a derivative is we want to relate X and Y. And luckily, we have a nice boxed equation in the red that perfectly relates X and Y right here in our constraint equation. And so what we're first going to do is we are going to solve that constraint equation for one of the variables, X or Y. Just because of how it's written, as well as just what we're used to, I'm going to take this equation, I'm going to solve it for Y by just subtracting the 2X over to the other side. And we get this nice and simple Y is equal to 30 minus 2 times X. And so that has to be true, right? We've used our constraint equation to show that, hey, this is our relationship between Y and X. If I know what X is, I can do 30 minus 2 times X, and that has to give me Y. So we might as well take this result and plug it into this equation, because that would eliminate Y. That would eliminate our Y variable. And so if we do that, what we'll see here, so I have my quantity that I'm labeling F. You could label it anything. You could label it smiley face if you wanted to. You could label it capital F. You could label it a big old G. You could label it whatever you wanted. I don't care. But here I'm labeling it F. That is X times Y squared. But I know what Y is. It's 30 minus 2X. So now I just do some simple algebra. I do some foiling out. So I square this term out. That gives me this. I distribute this X in, and then I've got a nice equation right there. And this is what I want to maximize. This right here is equivalent to this XY squared. It's just not in terms of X and Y. It's just only in terms of X. So there's my equation that I want to maximize. I want to make this as large as I possibly can. So we're going to have this sense of, let's take a derivative. Because if I take a derivative, as we've seen with the first derivative test, that can, it doesn't have to, but it can tell me where my maximums are. So we're gonna actually go ahead and take a derivative of F. And what we see here, so this was my F that we found before after I eliminated that Y variable. When I take a derivative, in this case, it's just simple power rule. Drop the 3 down, 4 times 3 gives me 12. Subtract 1 off that power, I get 2, so I got 12x squared. Same thing here, drop the 2, that 120 becomes a 240, subtract 1, I have an x. 900x just goes to 900. What you'll notice at this point here, I factor this quite a bit because I think it makes it a lot simpler to deal with. So I first factor out a 12, and now I just have this x squared minus 20x plus 75. Then at that point, this actually factors really nicely into 5 and 15. So I have 12 times x minus 5 times x minus 15. And now, remember what we've talked about. This whole idea of taking of finding a maximum or a minimum, right, to finding extrema, is to set f prime of x equal to 0, and then I'll sort of put on the side or endpoints, right? We haven't talked about endpoints yet. We'll get there in a bit. But really, this is the big thing that we're getting at here. I want to set f prime of x to 0 to find maximums. And really, when I'm doing that, what I'm hoping to have is I'm hoping to take this f prime right here that I've found, and I'm hoping to have, hey, 5, 15, and I don't know, maybe it ends up plus minus plus. I'm just guessing at that. I don't know exactly what that is off the top of my head, but maybe that's what we get. And I say, hey, there's a maximum and there's a minimum right there. Max, min, right there. And so, yeah, I just found where a maximum was. Awesome, right? And so that's what we can hope to do. Let's go ahead and actually set f prime equal to 0. As you could probably very clearly see, we just have this nice factored form. So when I set it equal to 0, I just get 5 and 15. So here's the question that we got to ask ourselves. All right, 5 and 15 are x values that make f prime equal to 0. But as we've very clearly seen, f prime can be 0 in a number of ways. F prime can be 0 in this case, which indicates a maximum. F prime can be 0 in, F prime can be 0 in this case, which indicates a minimum. And f prime can also be 0 in, let me draw a little more carefully, in that case, which indicates just nothing. There isn't an extrema. So we got to be careful here, because we don't exactly know. Just because f prime is 0, that doesn't mean that these are both maximums. Just because I say the word, hey, maximize in here, you can't just assume that these are going to yield maximums. And this is something that I guarantee you're going to want to be very careful with, because I can almost guarantee it that you'll skip this step. Let's say that we have a scenario here where instead of having 2 answers, you just get 1. So let's just cover this up. Let's just say you got 5. What you have to do here is you have to check to ensure that that is in fact a maximum. And there are a handful of ways to do this. You could take a second derivative and evaluate it at 5 and check your concavity. That's the second derivative test. That's totally fine. You could draw a number line and check on test points on either side of x equals 5 to see if in fact you get a max or a min. Also, before I say the third option, I just noticed a typo here. I flipped max and min there. Let me edit that. Min and max. So just as a call, I just edited those. I just flipped those. I had those written incorrectly. So recap, first 2 things. These could be, they could be mins, max, or nothing. And so the first 2 ways that you can check what the heck are they is you can do the second derivative test. So you can take the second derivative, evaluate it at these points, and that'll tell you whether it's a min or a max, or maybe even none. You could also do the first derivative test, which is just draw a number line, and you could look on test points on either side of these and see whether you get mins and maxes and or nothing. And then the third thing that you can do is probably the most hand wavy, but it's actually what I'm going to do here. And the reason I'm doing it here is just to show you this third way. What you can do is you can just evaluate 5 and 15 at the function. So what I'm going to do here, this will look weird. I'm gonna call out this f of x was equal to 4x cubed minus 120x squared plus 900x. And so what I'm actually going to do here is I'm just going to take 5 and 15, the 2 possible values, and I'm going to plug them both in here. And you'll see by this work right here, when I do that, when I plug in 5, I end up getting 2,000 for my quantity. For my quantity f, which is the one I'm trying to maximize. When I plug in 15, I end up with 0 right here. So I'd ask the question, well, okay, between 5 and 15, which of those is going to maximize the quantity f? And just by looking at this, I think it's pretty clear that this 2,000 is bigger than 0, right? And so 5 is going to maximize the quantity f right here. And remember, instead of xy squared, we had it sort of written differently, like here, equivalent but differently, just only in terms of x. So I plug in my 5, that's going to give me this really big 2,000. That indicates, that tells me with pretty good assurance that 5 is going to be the maximum there. Obviously, it's not super rigorous because we haven't used the first or the second derivative test, but this is in fact another way that you could do this. And so with here, we just say, yeah, hey, x equals 5 is going to maximize this function, because clearly 15 doesn't. 15 makes this function equal to 0. So we're not going to want to use that. We're going to want to say 5 here. Now that we have 5, we can go back to our constraint equation and we can solve for y, given that we now know x. So if I plug in 5 for x, this becomes 2 times 5 is 10. Subtract that over here. 30 minus 10 is my 20. Now I know the values of X and Y right there. The big note that I want to mention here, this problem did not take note of endpoints. I mentioned it a handful of times throughout this example, but we didn't actually do anything with them. If you're wondering why, don't bother with it for this example. We're going to do an application-based example where endpoints will make a lot more sense, and I'll explain them in that sense. For here, don't really worry about it too much. We'll just kind of pretend like they didn't exist, like we don't care about them, even though we probably should have. But for now, we won't worry about the lack of endpoint discussion in this example. So before I go into this application-based example, I'm actually going to jump to the end of this lecture really quick, and I'm going to go to, we have steps for optimization. I'm going to go through what we just did, and here I'm going to cross out some of these because they don't apply to that non-application-based example. We're not going to set up our optimization equation because we were given that. So basically, what we're saying here is you start off with an optimization equation, and that's what you're trying to optimize. That's what you're trying to maximize or minimize. Maybe maximize because you're talking about profits, maybe minimize if you're talking about cost. So what you're going to do is you're going to use the constraint equation. And remember here, we had a constraint equation that was 2x plus y equals 30. And our optimization equation was xy squared. That was the quantity we wanted to optimize. And so what we're going to do here is we're going to use that constraint equation to rewrite that optimization equation. That gave us that big polynomial. We're not going to worry about domain and range yet. That'll be more on the application-based example, so don't worry about that. We're going to set f prime equal to 0, and we're going to solve for our critical points. When we did that, we got x equals 5 and x equals 15. I'll label those x sub c equals 5 and x sub c equals 15. We didn't necessarily do the first and second derivative test. We can go ahead and cross that out from that past example. We just evaluated those critical points into the function, and that just gave us, for 5, we got a really big number, and for 15, we got a really small number. We got 0. That just tells me, hey, this is going to be my maximum, that big guy right there. And then there you go. And in terms of answering the actual question, right, I was asked for x and y, and so I actually have to say, hey, x is 5, and we did that quick little algebra, y is 20. So that's kind of how we did all that right there, just a quick little recap. Let's get rid of all this. We're going to come back to this later. So let's get on to this application-based example here. So let's say that we've got a supplier of screws, and they want to create a box for these screws. And a very, very key word in here is that box is going to be open. So it's going to be just like a normal box, like that you'd put in the mail. The top is going to be open. And how they're going to make this box is they're going to take a square piece of metal. It's going to be a 12-inch by 12-inch piece of metal. So we're going to have a square piece of metal here, and they're going to cut from each corner a tiny smaller square, and they're going to do that so that they can fold up the sides. So basically what this is going to look like is we're going to have this square here. They're going to actually just cut out right there, 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 and there, so that these shaded blue parts, they just fall off. They just go away. They disappear. We don't have them anymore. And now this section here, they're going to take it and they're going to fold it up. This section here, they're going to fold it up again, sort of out of the plane of the page, if you will. Sort of like, if you're looking at the screen, they're going to come out at the screen towards you. These 4 regions right here, they're going to sort of come out at you. And what that's going to give is that's going to give this box right here that now the top is open, right? That top is it doesn't have any sort of top lid, if you will. And so that's the scenario that's happening. Let's go back to the actual question. What we want to figure out is, so I've got this 12-inch by 12-inch. Ooh, that's not quite a square. That's not a square at all. So we've got this 12 by 12 piece of metal. We want to know, hey, how much do I cut out here? Do I cut out something like what I've shown in the red? Or am I going to cut out something more like in the orange that's maybe a lot smaller, right? So how big of an area should I cut out to make the volume of this resulting box as large as possible? This is a tough question. I won't skirt around that fact. This is a tough one here, and you have to be able to draw pictures. You got to be able to label things. You got to be able to look at these word problems and come up with these diagrams. And that's tough to do. I won't sugarcoat that at all. So let's take a look at this. We said that we have a 12 by 12 square cutout. So, and I'm actually going to draw this from scratch here. So we've got this nice big square cutout. Oh, that didn't work. Let's do that one more time. Come on. I want to get that looking like a nice square. There we go. So we've got a nice square right there. And what we know is that it is 12 by 12. Let's label that in red, a little darker of a color. So we've got 12 for this length right here, and we've got 12 for that length right there. So this whole square is 12 by 12. That's great. We know that. And now what we're going to do, as we said, we're going to cut out a section here, a square section on each of these corners. And obviously the question here is, how big should we cut these corners? And so what I'm going to mention here is, well, the problem statement says, hey, let's cut these corners to a size that maximizes our volume. So I don't know exactly what these corners are, but really the point is that it's kind of good that I don't know, because that's what I'm looking for. That's what we're trying to find. So what I'm actually going to do is I am going to label this length as X. And again, because these corners are square cutouts, they'll both be X on that side. So if that's X and that's X, I'll label a couple more of these here, X and X. I could label those down here as well, but I'm not going to bother. So I've got X and X right there. So X is really what we're looking for. The answer to our question at the very end, right? We were being asked what size square should be cut from each corner. So the answer to our question will be X. That's great. We now know at the very end, I better state X equals 7 or whatever it ends up being. And that's my answer right there. So we're not done labeling stuff here. I can actually label another dimension here. And this other dimension, let's label this in orange, is going to be this length right here. And so just by doing a little bit of math right here, I see, hey, this whole thing is 12. This is X and this is X. So this right here in the middle is going to be 12 minus 2X right there. Whatever X is, that middle has to be 12 minus 2 times X. So for example, if X were 1, then really what we've got here is we've got a length of 1 and a length of 1. So in order for the whole length to be 12, this in the middle has to be 10. So like a 10, 1, and 1. That would add up to 12. And then likewise, if these outsides were 2, then this in the middle would have to be 8. That would get me to a full length of 12. And now here's actually where our constraints are going to come in. Let's say that X was 7. So let's say, in fact, I'm going to go ahead and write this off to the side here in purple. Let's say X is 7. Well, then what we've got here is we've got a length of 7, and we've got a length of 7. So that adds up to 14. But remember, we need the whole length to add up to 12. So this length in here should be -2. I put a big question mark next to that. That seems weird. We can't have a negative length here. So what we're seeing is that if x is equal to 7, that just doesn't work. That just doesn't make sense, right? You can think about this as well, right? If this whole length is 12, half of it is going to be 6. So if you cut out a 7-inch square, you're going to be cutting out something that looks, like this, for example. You're going to be cutting out all of that in there. And that's just bigger than we could possibly cut out. Because if I cut that out, then I'm also going to try and cut that out, and you can't. It's already, part of it's already been cut right in there. So weird things happen there if like x is 7, for example. And what we'll notice is that really weird things happen the moment that x hits a value of 6 here. If x is 6, then basically what's happening, that middle length is 0. And again, that doesn't make any sense. What's going on in that scenario, I'll draw sort of a smaller square here. If this whole length is 12, and I cut out 6 inches from each side, I'm making my cut right there, 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 and there, which says, hey, I'm cutting out this square, cutting out that square. I'm just cutting out the whole thing. And now I don't have a box anymore. I just have 4 random pieces of metal that I'm cutting. And so what we're saying here is when x is equal to 6, that's bad. That doesn't help us. We've just cut our square into our big square into 4 smaller squares. That doesn't produce a box at all. There's nothing to even fold up anymore. The other weird thing happens when x is equal to 0. So if x were equal to 0, then this in the middle has to be 12 in order for that entire length to be 12. And so what this just means is we don't cut anything. If we just don't cut, if x is 0, that means that we don't actually cut out these blue dashed squares here. We don't cut anything. And so, well, now we just have a piece of sheet metal and we don't have any corners to fold up. We don't have any sides to fold up because we didn't cut our corners at all. So what we're seeing here is that x equals 0 and x equals 6, we'll just say weird. Weird things happen in those scenarios. And so we got to be careful there. So we've got this square. Let's draw another picture here. So what happens when we actually fold this square up? Let's be careful about how we draw this. So we've got all that right there, putting in that background there. So remember now, we took these sides here, these corners, and we cut them out. And then this part right here, that's the length that we are going to fold up sort of out of the screen, if you will, sort of towards your face, as you're looking at the screen. We're going to fold that up. And now what's going to happen is this right in here is going to be the sort of floor of this box. It's going to be the bottom of that box. And so what you can see is that this has a length of 12 minus 2x. This has a length of 12 minus 2x. So our box here is going to have a length and a width of 12 minus 2x. And then lastly, we look here, we say, well, how much did we fold it up? Well, if you look, if I take this guy and I fold this sort of up that way, right, so that it's coming out of the page, this is the height of that folded part, right? And so that length is x right there. We know that length to be x. And so this height right here is going to be x. So right there, we've got the dimensions of our box right here. Let's go ahead. I'll clean this up just a little bit. Don't need any of that. So we've got the dimensions for our box. As you could probably presume, we're going to go on and we're going to start doing derivatives and maximums and mins. But here's what I want to mention. I want to go back to that idea of that x being 0 and x being 6. And if we look at this box, obviously, if x is 0, we don't have a height of our box. It just doesn't work. Our box just has no height. And if x is 6, you'll notice that when x is 6, this that I'm underlining is equal to 0, which means that we don't have a length or a width to our box. It's just not a box. So what I'm going to do here is I'm going to write out our volume is going to be x times 12 minus 2x squared. That's length times width times height. What I want to do here in terms of endpoints, I want to take a look at this guy and I want to look at its domain. And domain should be something that we're comfortable with here, being in calculus. So when I look at domain, what we need to recognize is that in a real world scenario, I am going to require that v of x be greater than or equal to 0, because volume can't be negative. If I hand you a box and I say this box has negative volume, that just doesn't make sense. Volume is not something that can be negative. And so this sort of real life situation, this real life constraint, forces us to make f of x be greater than or equal to 0. And if we look at this guy, at this inequality right here, we should be able to solve that and recognize that two things have to happen. X has to be greater than or equal to 0, or 12 minus 2x has to be greater than 0 as well. And so I'll simplify this right here. 12 has to be less or greater than 2x. X has to be less than or equal to 6. So really what we're seeing here is that x has to be greater than 0 and x has to be less than 6. And so that right there is giving us our conditions on what x is allowed to be. And those conditions they come from this real life situation. Again, look at this box, right? If I told you that a box has a height of x and you make x -4, that just doesn't make sense. You can't have a box with negative height. A height can't be negative. And likewise, if you made x equal to 7, that's saying that this width right here and this length, that both this length and this width, if x is equal to 7, this length and width would be -2, and that just doesn't make sense. So 0 and 6 are our situational restrictions, these real life restrictions that we have on the value of x. And so what that tells me is, it tells me endpoints. It says endpoints. Remember, we've talked about f prime being 0 or endpoints. And we'll say x equals 0 and x equals 6 are our endpoints here. And so there we go. We're going to want to make sure we keep track of those and remember those. That makes sure that our box has positive dimensions. So now that we've done all this setup, honestly, we've really done the hard part here. Now we are trying to maximize volume that was stated in the problem statement. We want to maximize volume, and luckily, just by doing length times width times height, we have a volume equation. So guess what we can do? We can take our volume equation and we can do two things to it. We can take a derivative of it and set that derivative equal to 0 to find critical points. And we can also evaluate our endpoints. And because remember, we can have maxes or minimums at either endpoints or when f prime is equal to 0. So we're going to do both of them. Let's go ahead and start off. I'm going to take this volume equation, and I'm going to go ahead and write out v of x equals x times 12 minus 2x squared. What I'll tell you is that if you FOIL this out, you're going to get 4x cubed minus 48x squared plus 144x. That's just, I'm saving a little bit of time there, just skipping all that detailed work, but that's what you get there. So now when we go to take our derivative, we're going to say v prime is equal to 12x squared simple product, or excuse me, simple power rule right there, minus 96x plus 144. Then we're going to do some awesome factoring. Let's factor out a 12 right there. And then lastly, we can factor this one more time. And then so what we're seeing here is that if we go ahead and set v prime equal to 0, I'm going to have 0 equals 12 times x minus 2 times x minus 6, because that's my v prime. And that is going to give me two answers. X critical 1 is 2, and x critical 2 is 6 right there. So these are my critical points. We're obviously not done, but I'll box them because they're important. So those are our critical points, and those came from evaluating v prime is equal to 0. Our function that we wanted to maximize was v. And so we took a derivative of it. We set it equal to 0. This gives us our critical points. Now, here's what we could do. And I'm actually going to go ahead and do this in multiple ways, just to be very clear. I'm going to make a number line here. So I'm going to make a number line. Let's move this down a little bit. We have v prime of x is equal to 12 times x minus 2 times x minus 6. So that's my v prime. And I'm going to make a number line. I'm going to label it v prime of x, and I'm going to mark my critical points here, 2 and 6. And then what I'm going to do is I'm going to evaluate some test points. I'm going to pick 0, and I'm going to pick 8 right here, and I'm going to also pick 4 as the points that I'm going to test. When I do that, when I test 0, we can look here. Well, 12 is positive. 0 minus 2 is negative, and 0 minus 6 is negative. So I end up having a positive times a negative times a negative. That yields a positive. So in fact, I have a plus right up there. Let's do that in a different color. I have a plus right there. If I plug in 4 in for x up here, if I do v prime of 4, I'm going to have 12, which again is positive, times 4 minus 2, which is positive, times 4 minus 6, which is negative. So I have a positive, and a negative. That is going to overall yield a negative. And then lastly, we're going to see that I get a positive if I plug in 8. So I have a positive there. If I plug in 8 here, that's going to be positive. And if I plug in 8 there, that's going to be positive. So the result is going to be positive there. So when I'm looking at this, I'm looking at this and I'm saying, all right, so you're telling me I'm going up, and then I start going down, and then I start going up again. This to me seems like at 2, I have a max, and at 6, I have a min. And in fact, that actually is the case right here. In order to maximize this, we set x equal to 2. That actually works. You've proven this. Boom, right there, done. Except for the fact that we haven't worried about our endpoints yet. And I'm going to pause and I'll get back to that later. But just what I want to show you for the f prime values for our critical points, this is a perfectly viable way of doing this. What you also could do, and I'm not going to do this, but you could do the second derivative test. So I could go ahead and I could take v double prime, and basically I could evaluate v double prime of 2, and I could evaluate v double prime of 6, and I could just say, hey, what are these equal to? Are they positive or are they negative? And I guarantee you for 2, you're going to get here that v double prime of 2 is less than 0. And here you're going to get v double prime of 6 is greater than 0, indicating respectively concave down and concave up. And so you could take the second derivative there, or you could do what I'm going to call my new favorite way. I could just plug in points into the original function, right? When we get these critical points here, we're already at a scenario where we're thinking, okay, 2 and 6 are probably, it's probably either 2 or 6 is my answer. That's probably the answer. And so, or maybe 0, right? Because of endpoints. So really we'd say, hey, endpoints are 0 and 6, right? We looked at that. So endpoints are 0 and 6. So my answer is it's probably 0 or 6 or 2 or 6 again. So it's one of those. So why don't we just do this? Why don't we just evaluate the volume? We have v of x is equal to 4x cubed minus 48x squared plus 144x. This is a different format of what we saw originally. You could also write it as x times 12 minus 2x squared. Either way is fine. But why don't we just do this? Why don't we just do v of 0, v of 2, and v of 6 and just see what our answer is? Just see which one is the biggest, right? Because we already know that the only time that we're going to have a maximum, the only time we're going to have an extrema is at either an endpoint or at a critical point. And so if I just plug all of these in and I see what I get, then we're done. And we just know we just see which one is the biggest. And I actually do that over here. Let's skip to that. I actually do that right here. I evaluate both of my critical points. I do v of 2 and v of 6, and I get 128 cubic inches and I get 0 cubic inches. And then also I evaluate my endpoints, 0 and 6, and I get 0 in these scenarios. So obviously we're looking at this saying, okay, 2 is going to be our answer. You should cut 2-inch squares from the corner. Yay, we're done. That's our answer there. So what I want to make very clear here, though, is this scenario right here. When v is 0 and v is 6, we talked about this before. We said that, hey, look, take a look at this box right here. This length is x. If x is equal to 0, that's a box with no height, meaning the box is not a box. It's just a flat square, which means that the volume is 0. And then likewise, if I set the length and the width equal to 0, which is done by setting x equal to 6, you can just plug x equals 6 into each of these, and you can see that these become 0 when x is 6. So if the length and width are 0, that again just means I don't have a box. My volume is 0. So when we test our endpoints in this scenario, we end up just getting 0, which is just saying, hey, there's no box anymore. And so endpoints are not going to give us a maximum. In fact, they're going to give us a minimum, right? Maybe if you were, if you were trying to sabotage this, this company that was making these boxes, and you said, I'm going to make them, have a minimum volume, then, well, you just wouldn't cut any squares out. You'd set x equal to 0. Remember, x is this length right here. You just wouldn't cut any x's out. You set x equal to 0, and then they can't fold the squares. They can't fold this. There's no sides to fold up. They can't fold this part up right here. And so they just can't make a box. And so, they have 0 volume boxes, and they can't put any screws in there because they're just going to fall out. Or what you would do is you would make x equal to 6, which is this halfway point right there. And then you're just cutting out 4 giant squares from this whole thing. And now you don't even have a box. If you just cut right through there, now you just have 4 smaller squares, no box. Yay, you don't have a box. You have a minimum volume of nothing. But if you go right nice in the middle and you cut them at 2 inches here and 2 inches there, then you're going to get this awesome maximum volume of 128. Yeah, let me explain sort of so we've got these different ways that we could do this. We found our critical points, and I first said, hey, let's do a first derivative test, and we did it, and we said, yeah, max at 2, good. 2 is our answer, done. But the reason that I like to do this method here, where I plug in my values, is because what if I asked you, hey, what is the maximum volume? Not what X value, hey, how should I cut them? How should I cut the squares? But what if I asked you, what is the maximum volume that can be made? You have to answer with 128. And so you have to do this work anyways. You have to do all this evaluation and algebra anyways. So I might as well just do it there. So that's going to be the way that at least you'll see me do these problems. I'll actually just take my endpoints, in this case 0 and 6, and I'll take my critical points, again in this case 2 and 6, and I'll just evaluate the function at each of those. I'll just see which one's the biggest. Maximum. Boom. There you go. If I asked for minimum instead of maximum, you'd just give me one of these, 0 or 6, and that'd be your answer. So x equals 2. There we go. Cut the corners to be 2 inches on each side. So wrapping all this up, getting into these steps again, and I'll relate this to this example that we just did. We're going to first start by drawing a diagram if it applies to the situation. So I give you a word problem. In this case, we had that box, right? We had that. So we had let's go ahead and draw it really quickly. We had this sheet right here, and we were going to cut out these little squares from it. And when we do that, that's going to end up yielding a nice box right there. And that's going to give us, that's sort of the diagrams for this scenario. We label accordingly on our diagrams, obviously, label variables, label things like that. Then we figure out what we're trying to optimize. In this problem, I just told you, hey, we're optimizing volume. I want the max volume. I didn't tell you what the volume equation was, so we had to come up with that. And so what we then stated was that v of x, you could call it f if you want. I called it v just because it was volume. We came up with our x times 12 minus 2x squared. That's what we're trying to optimize. That's our optimization equation. Our constraint equation, in this case, we didn't really have one, and that's why I put if necessary. There wasn't even two variables here to deal with. We didn't have to bother with like an x and a y. So in this case, we actually didn't have to rewrite f using our constraint equation. We didn't have to use that constraint equation to rewrite our optimization equation. So that didn't apply here in this example. Find the domain and range of f. And remember, just these are general steps. I'm saying f, but in our problem, it was v. We looked at the domain of x times 12 minus 2x squared in this case. And we found that x had to be greater than 0 because our dimension has to be positive. And x can't be bigger than 6 because if it was, you'd be cutting out more than you possibly could out of this sheet metal square. And so that gave us restrictions on x. That gave us our endpoints that we see down here. X equals 0 and x equals 6. The next step was to set f prime equal to 0. So we took this volume equation, we took a derivative of it, we set it equal to 0, we solved for our critical points. And when we did that, we got xc equals 2 and we got xc equals 6. And then, like I said, like I offered as an alternative, you can do the first or the second derivative test to check those critical points. And we did that, we did our number line. And then you can actually evaluate these critical points and the endpoints. And remember, we did that right here. I evaluated critical points, 2 and 6, and I evaluated endpoints, 0 and 6. And that told me which was the largest of all of them. And we did that, and that told us our answer there. And then you actually answer the question, right? You actually make sure that you answer exactly what is being asked of you. In this case, it said, how big of squares should we cut? So you say, hey, cut the squares to 2 inches. One thing I want to mention that didn't apply here is this word global right here. I want to go back here. Let's say that let's keep going back. Let's say that we did this first derivative test and you ended up with a scenario where you had multiple maximums. In this case here, we obviously just had one max and one min, but let's say that you had a scenario where you had multiple maximums. The question is then which maximum is actually larger than the other, right? You've got two maximums, but they don't necessarily have to go to the exact same height, right? You could have a max go up there, and you have a min, you have another max go right there. And then this is our answer. We don't want to take this guy right here. That'd be bad because that's not our full global maximum. That's yet again another reason why we like to do this work right here, is by just manually just raw plugging in the numbers into our volume function. We get a bunch of volumes out. We just see which one is the biggest. And there you go. That's your answer. So that's why I mentioned global right here. We'll see several examples of that on the worksheet. So I'm going to go ahead and leave that there for the lecture. Make sure to study it up. This is definitely, optimization is definitely one of the toughest calc concepts of the semester. So make sure you're up to snuff on this, and we'll go ahead and call that the lecture there.